Alright, ladies and gentlemen, this is going to be our next video on the unique properties of water. So let's get started on this next video. So let's go through and look at what a phase change is. Now, a phase change is going to be a change from one state to another. So from a solid to a liquid, to a liquid to a gas, from a solid to a gas, liquid to solid, gas to solid, etc. So this is going to be a change without a chemical composition change of whatever we're going through and talking about. So other words that we can call this are phase transition, a physical change, or a state change. Now, phase changes are going to be really, really important for us to understand with water. Now, water exists in three different forms. We have the solid, which is the ice. We have the liquid, which is going to be the liquid water that we think of. And then it can exist in a gas or water vapor state. And dependent upon how we increase or decrease the temperature, we can get different phase changes with water. Now, when you increase or decrease the temperature of a substance, you're going to force that substance into what we call a phase change. The other thing we have to think about is pressure might also affect phase changes. And when you get into a chemistry course, pressure and temperature are the two variables that affect the changes of water and other substances from a solid to a liquid to a gas. So let's go through and look at the density of water as water goes through phase changes here. So let's compare the density of solid water and liquid water. So let's say I take a beaker and I fill that beaker up with some water. Now I'm going to take that beaker and put it in the freezer for maybe 3 or 4 minutes. And what we're going to see is on the surface of that water, we're going to get ice forming. Now let's go through and zoom into the molecular level of the liquid water and the molecular level of the solid ice here, or the solid water. What we're going to see are two different formations of the water molecules within the solid ice and the liquid water. So if we go through and look at the solid ice here, what we can see is the water molecules, these H2O molecules, are nicely aligned in this crystalline structure. But if we look at the liquid water, they're not as aligned and they can kind of flow amongst each other. This is going to affect the density of the water and how the water goes through and forms dependent upon if it's a solid or a liquid. So the expansion on freezing water is going to form a crystalline structure that when it expands creates a less dense state than the liquid water. That's why the ice is going to float when we go through and put it in liquid water. Now this is going to be really important when we talk about winter stagnation. And what ice does is actually creates a blanket and keeps the warmer depths of the ponds or lakes that exist in an ecosystem warm, so that way the organisms can stay alive in those liquid water habitats. Now remember, there are 3 states of water here. So the first one is going to be ice. So when water freezes, the molecules move so slowly that the hydrogen bonds between them, which we're going to learn about soon, lock each molecule in place and form a crystal. So if we look at this, what we can see, let's go through some levels of a water column. Let's say we're in the ocean. And I'll go through, we'll put in some clouds, maybe an iceberg here. When we're talking about solid ice, remember, the structure is going to look like this. But again, this solid ice is going to cause the molecules to move slowly, creating a crystalline structure that is less dense than the liquid states of those waters. So remember, the ice is less dense than the liquid water, which is why icebergs go through and float when we go through and put them in the ocean, or we see them and observe them in the ocean. Now, the other phase that we're going to have to talk about is liquid water. So this is when hydrogen bonds hold most of the water molecules together in smaller clusters or groups, but it's going to maintain the fluidity of that water. So hydrogen bonds in liquid water are constantly being broken and reformed, which is why the water doesn't hold that solid structure. Now, if we were to go through a water column, warm water is going to be less dense because the molecules are spread out a little bit more, and they're going through and breaking and reforming those bonds a little bit faster. Whereas if we were to go through and look at colder water, let's say water that is more dense and deeper, this is going to be more dense because they're moving slower, they have less energy, and they're packed a little bit tighter together. So if we were to look at water columns here, we can see the warmer water generally is going to be at the surface, and the colder water is going to be further down within water columns because of this density property that goes through and affects liquid water. Now let's go through and talk about the energy of the different phases of water here. So what we can see is we have gas or water vapors here, and gaseous water vapor is going to have the most energy and vibrating the most. So the hydrogen bonds between the molecules here are going to be breaking and reforming much quicker because it has the most amount of energy. Now, liquid water is going to look like this. And liquid water is going to have a vibrational or energy pattern somewhere in the middle. So the bonds are going to be breaking and reforming less than the gaseous or water vapor state, but more than the solid state or the crystalline structure that we see in ice. So solid ice is going to have the least amount of energy, and in this case, it's going to be vibrating the least. So it's going to be forming and breaking these bonds much slower compared to the liquid and the gas phases of water molecules. Now, the last phase that we're going to go through and talk about water is the gas or vapor state of water. So when a water molecule moves fast enough, it breaks free of all of the hydrogen bonds and becomes a gas. Now, not all of the hydrogen bonds are broken. There are still going to be some hydrogen bonds going through, but there's going to be much less because the gaseous state has much more energy. So if we think about this, well, water molecules are spread much further apart than in the liquid, and the density is actually going to be the least. So if we increase the temperature, we're going to also increase the rate of evaporation. Remember, evaporation is going from liquid water to gaseous or water vapor state. So we can see that as we're going through our phase changes, we can see that as the temperature goes through and increases and decreases, we can go through, affect the density of the water, and affect the energy that these water molecules possess, just based on the temperature. Now, the last thing that we have to go through and talk about is water and heat, and specifically heat capacity. So heat capacity is the amount of heat needed to raise the temperature of a substance 1 degrees. In this case, we'll talk either Kelvin or Celsius. So let's go through and look at a graph here. Now, on the y-axis, we're going to have, in this case, temperature as we're going through and changing. So I have Celsius and Fahrenheit here. And then on the x-axis, we're going to have time. And we can represent water going through phase changes here based on this graph of the temperature and really the heat. And what I want you guys to keep in mind is when I'm talking about heat and I'm talking about temperature, I'm really talking about the amount of energy. Temperature is just a measure really of the amount of energy that a substance has. And heat, remember, is a form of energy. So as we're looking through this heating curve here, we can see that we're going to start off with solid ice. So as we go through and add heat to the system here, we're going to see the ice go through a phase change. And from ice, it's going to turn into water. So anywhere from 32 degrees Fahrenheit to 212 degrees Fahrenheit, or 0 degrees Celsius to 100 degrees Celsius, we're going to see, based on this temperature, water exist in its liquid state. And if it's 0 degrees Celsius or 32 degrees Fahrenheit or below, it's going to exist as ice. Now again, once we reach this threshold here and we continue to add heat energy, we can get water to go through another phase change here. So as we go from 100 degrees Celsius or 212 degrees Fahrenheit beyond, it's going to exist in its gaseous phase. So water has the highest heat capacity of any natural substance, or that's the amount of energy needed to raise the temperature of the substance, or the amount of energy needed to get it to go through a phase change. So if we want water to go from ice to a liquid, so from a solid to a liquid here, we have to put in an incredible amount of energy compared to other substances on the planet. Same thing if we want to go from liquid water to gaseous water vapors. Now, heat energy must be used to break hydrogen bonds between water molecules before the molecules are able to move faster and increase temperature. So we can see where the graph has those flat lines, that's where we're adding heat energy to break the hydrogen bonds to get it to transition from either a solid to a liquid or from a liquid to a gas. So as we go back to the graph here, remember, ice is going to have the least amount of energy. Water is going to be somewhere in the middle, or the liquid phase of water, and the gas vapor or the water vapor state is going to have the most. So as we go through and add heat, we can see heat, remember, is energy. We're adding that energy to that system. What we can see here is the energy of each of those molecules is going to increase, breaking those hydrogen bonds and causing the phase changes to occur. So why is this important? Well, water has really high heat capacity. And why is it so high for water? Well, in this case, because of the multiple hydrogen bonds existing between the water molecules, it takes lots and lots of energy to make the molecules move faster. So we have to go through and add a lot of energy. And by raising the temperature, remember, we're increasing the quantity of energy. And the more we want the molecules to move faster, the more energy we have to add. So when we're talking about intermolecular forces, which we'll look at in the next video here, hydrogen bonds are extremely strong bonds that exist between water molecules. They're different than ionic and covalent bonds. They're intermolecular forces. And because of that, water has this really, really high heat capacity. So large bodies of water, such as oceans and lakes, can absorb large amounts of heat with only small changes in temperature. If you ever go down to the beach in New Jersey or New York in September and October, the actual water temperature still remains in the 70s or 80s sometimes, but the air temperature can be in the 60s, 50s, or even 40s. And the other thing that we can see here is this is going to protect the organisms that are living in these environments from drastic temperature changes. So while the fish living in the oceans depend upon certain temperatures and stable temperatures within oceans and lakes in order to maintain homeostasis and continue to live. So again, why are we going through and learning this? Well, homeostasis, remember, is an organism's ability to maintain constant and stable internal conditions. So remember, a lot of organisms are made out of large quantities of water here, and the temperature of these organisms, remember, if you get a fever, that can be potentially fatal if your body gets too high in temperature, because what it does is cause degradation of the proteins and enzymes in your body. So it takes a long time to heat up a lot of energy of water and to really go through and effectively cool it down as well. So water's high heat capacity is protecting organisms that live in water environments and organisms that are made out of water from drastic changes in temperature. So this heat capacity is going through and protecting these organisms and allowing them to continue to maintain homeostasis within their bodies and then within their environments. So as an example here, if I take a goldfish and put it in colder water, well, the goldfish isn't going to instantaneously go through and no longer maintain homeostasis because of its ability to internally control body temperature. And if I go through and heat up the water, well, the goldfish isn't going to instantaneously go through and no longer maintain homeostasis because, again, of these water conditions. But if I change the water too much or the body of water is too small, in that case, the goldfish might die. So the thing we have to keep in mind is when we're talking about oceans and we're talking about the bodies of oceans, one, the size of the water is going to affect organisms that live in that water column. And then the quantity of water that exists in the organism's bodies is also going to have an effect on internal temperature. So did you guys learn? Well, did you learn a couple of things? Did you learn the density of water and the phase changes that exist among solid, liquid, and gaseous state water? Did you guys learn about water and its relationship to energy? Remember, heat and temperature. Temperature is a measure of the amount of heat, and heat is really just energy. So temperature, theoretically, is just going through and measuring energy. And did you guys go through and learn about water and heat capacity and why this heat capacity is both important inside organisms' bodies, but also in the ecosystems that they live in? This is going to be the end of the video. I will see you guys in class tomorrow.